we looked at a Taylor polynomial for the natural log of x centered at 1. And we calculated P4 in the last lesson. So I'm going to flip back to that last lesson and get that information. So here was the Taylor polynomial centered at 1 for a P4, fourth degree polynomial for natural log. So if you remember, we calculated the derivatives and came up with the expression for that polynomial expression there. And so let me just kind of dump that into here, and we can kind of scale that down a little bit. Okay, so there's that polynomial expression. So that polynomial, that P4, looks kind of like that polynomial approximation looks like this. So we have 0, and then we have plus 1 x minus 1 minus x minus 1 squared over 2 factorial plus 2 times x minus 1 cubed over 3 factorial minus 6x minus 1 to the 4th over 4 factorial. So that is the expression for the approximation. And in looking at that, we had these coefficients 2 and 6 here. If we simplify that a little bit, we can start to see a pattern emerge here. So rewriting this, I'm going to rewrite this without factorials, just so that we can kind of see the pattern here that emerges when we're talking about natural log. So instead of 3 factorial, I'm going to write 3 times 2 times 1. Instead of 2 factorial, I wrote 2 times 1. Instead of 4 factorial, I'm going to write 4 times 3 times 2 times 1. And so as we look at that that polynomial expression, we can kind of see that we have a 2 in the numerator here, and that will cancel with the 2 in the denominator here. So we're just kind of simplifying a little bit. A 6 in the numerator here will cancel with the 3 and the 2 there. And so we end up having this polynomial approximation that really looks like x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over what's left here is 3 minus x minus 1 to the 4th over what's left in the denominator here is 4. And so we start to see this this pattern emerge where we have just the approximation degree in the denominator. The factorials are starting to cancel out. And so this is the 4th degree polynomial approximation for the natural log of x. Sorry about that. Centered about 1. So I'm going to kind of take that and put that up here for the time being. And I just want to get rid of this here. So let me ungroup this real quick. And regroup this real quick. I didn't group it enough. There we go. So group that up. Just want to get rid of this sort of stuff there. There we go. Okay. So there's the polynomial approximation for natural log of x centered at 1. And so if we kind of look at this on the graphing calculator, here's our natural log of x. So there's our natural log of x graph. Okay, I'm going to go ahead and put the polynomial approximation below that. So we have x minus 1 minus x minus 1 squared divided by 2 plus the quantity x minus 1 cubed divided by 3 minus quantity x minus 1 to the 4th divided by 4. And so as we look at that polynomial approximation, let's just take the original non-polynomial function and make it dark. There's the original non-polynomial function. Here is the 4th degree approximation. That 4th degree approximation is pretty accurate. It looks like from about 0 to maybe 2 or 3. So if we take a look at that, maybe we'll go out to 5 here. Then there we go. So we start to see that we have this 4th degree approximation that looks pretty good, you know, from about here to about here. That approximation pretty much follows the actual function pretty closely. And so if we start to look at using this approximation to evaluate different values of x, then we can we'll look at a table in just a second, but you know, if we take a look at the natural log of 1, the actual value of that function is 0. So we're looking right here at this point. The value at 1 of the polynomial also ends up being 0, right? If we put a 1 in for x and all of these things, we end up getting 0. So that goes back to that first rule that we need the polynomial approximation to match the value of the actual function at the function. Anything else just wouldn't be that accurate. And so now if we would take the natural log of 1.25 and calculate that, and then put 1.25 in for each one of these values in x to calculate an approximation, then to do that we can just look at the tables here. So we're going to go ahead and reset the table. We'll have it start at 1 and we'll have it increment by 0.25. And when we look at that table, then we start to see those values for y1 and y2. So we have 0.22314, 0.22314 is the actual value of the natural log. The approximation is 0.22298. For 1.5, we're at 0.40547, and for the approximation, we're at 0.40104. I put that in the wrong spot. 0.40104, and so we see that, you know, at 1.5, that approximation at 1.5 is slightly lower than the actual value of the function. And then at 1.75, we're looking at an actual value of 0.55 0.962. And the approximation here is 0.53027, 0.53027. So you know, we're starting to see that gap widening between the actual value and the approximate value as we follow this fourth degree approximation farther and farther away from the center of 1. Remember, here's the center of 1. So as we get the bigger and bigger values out here, we're going to start to see this discrepancy between the actual value and the P4 estimate, the fourth degree polynomial estimate, increase, that gap widen. And so as we look at 2 here, we get 0.69315. And the approximation is 0.58333. You can see that disparity gets bigger and bigger and bigger to the point where if we come out here at a value of x equals 3, we can see that our actual value, the natural log of 3, is up here, but our approximate value, if we would use our P4 approximation, our approximate value would be way down here. So that would be your P4 for the value of 3, where this would be your natural log of 3. So that gap widens as we see that fourth degree polynomial start to deviate from the natural log curve. So if we take a look at that, then here's a close-up value of that. If we take a look at that P3, that natural log of 3, we can see that natural log of 3 is, I'll have to kind of, there we go, 1.0986. So the natural log of 3 is 1.0986, whereas the polynomial approximation is negative 2.892. So that approximation is, you know, we're way down here on that approximation. So we can see that disparity starts to really widen the gap. So what we really are looking at then is to get a feel for this error here, this remainder. You know, how far off are we from the actual value here? And of course, it's going to depend upon how far away from the center we are. And so we're going to get a feel for that on this next page here. And that is, we're going to take this and say, well, what is our error? If we have an approximation of, if we want to approximate the natural log of 1.5, so if we know the actual value here, the actual value, and we do because we want to evaluate the function at 1.5. And so if we evaluate the function at 1.5, that's taking the natural log of 1.5. And so if we look at the natural log of 1.5, the natural log of 1.5 is right there. So that natural log of 1.5 is equal to 0.4547. And the fourth degree approximation at 1.5 is 0.40104. And so if we look at the exact value of the error, all we have to do is we just have to take the value of the function and subtract from it the value of the approximation. And so when we subtract those two numbers, which are right here, when we subtract those two numbers, we end up getting the natural log is 0.40547. The approximation is 0.40104. So when we subtract those two, 0.40547 minus 0.40104, 40104, there's a difference of 0.00443. So there's the error. And when we think of the error, we think of the absolute value of the difference of that. So even if we switched those and subtracted the approximation from the natural log, we get the negative of that value. So then we come to talk about, well, what if we want to take a look at the error, and we want to look at maximizing that error. And if we want to look at maximizing that error, finding that maximum value of the error, then we have to look at something that's called Taylor's theorem. And we have to look at this remainder here. And this remainder, if you look at this, we're talking about, you know, a Taylor's pattern here where we have the derivative divided by the factorial times x to the same power as that polynomial is. And so this remainder here then is really what comes after the values that are part of your approximation. And so this remainder then is going to be just this next term, and this next term is going to be evaluated at a value z, and value z is either going to be the value of the center c, or the value of x, depending upon which one maximizes the ratio. So we just have to figure out which one will maximize that expression. And so when we look at maximizing this error here, we're saying let's take the derivative, the next derivative basically. And so when we take a look at that for a fourth degree polynomial, for a P4 of x, in this case a P4 of 1, then the remainder is going to be that fifth derivative evaluated at some value c over n plus 1, which is the next factorial, times x minus c raised to that next power. And so that's going to be our remainder for our nth degree approximation. So a remainder for the fourth degree approximation is this next term that has the fifth degree polynomial expression in it. So this one would be in N4, or excuse me, in R4, a fourth degree remainder. And so what we need then is we need the value of the next derivative here. So if we look at the value of our derivatives, our fourth derivative was minus 6x to the minus 4. So we'll take that information to get the next derivative here. So our f4 of x was negative 6x to the minus 4. So our fifth derivative of x then is 24x to the minus 5. That's just taking the derivative one more time. So now we ask ourselves, well, this is really our f, so our f of z. Okay, we have to maximize this in that numerator. So of this, in fact, I'm just going to go back and touch that up a little bit and get rid of that and rewrite it. So this is really our f of z. And so which one maximizes? We're looking for a max here. Is it going to be f of c, or is it going to be f of x? Which one is going to be the fifth derivative evaluated at c, or the fifth derivative evaluated at x? that's what's going to go in for this f of z. So in that case, we have a 24, and c, the center is 1, so it's 1 to the minus 1/5 power. And x, which is 24, and x is 1.5 to the minus 5th power. And so this one is the maximum here, because the minus 5th means it's in the denominator, right? This is 24 over 1 to the 5th. This is 24 over 1.5 to the 5th. So this is our maximum value. And so, there we go. If this is our maximum value, then that's the value that goes right here. And so our maximum remainder then is 24, 1 to the 5th is just 1, so 24 times x is 1.5 minus c, center of 1, to the 5th power, right? 4 plus 1 is 5, so we have 4 plus 1 here, all over 4 plus 1, or 5 factorial. So there's the maximum value of the error. So that ends up being 24 times 0.5 to the 5th over 5 factorial, which ends up being 1 over 160. So that is 0.00625. And so if we notice, that's our maximum value. We call that that's the remainder for the 4th degree polynomial. And that's as big as it can be. That's a maximum value. So if we look at this, our actual remainder was 0.00443, which is smaller than 0.00625. So this maximizes it. This will find our maximum error for us. And the reason why that's important is because if this maximum error is tolerable, you know, if you can tolerate that much error, then we know for sure that the actual error is going to be smaller. So looking at this idea of finding an error, we can see that when we want to maximize the error and use the Taylor theorem here for finding the maximum error, we want to be sure that we consider what value of z makes this expression the biggest. And so when we're looking at this, we know that for a 4th degree approximation, we're going to have an error of basically 4 1/1000ths. And we're looking at a maximum error when we figure out what makes this a maximum of about 6 1/1000ths. So if we just kind of summarize what we're looking at here, we've got for a P4, we've got a max error of 0.00625, so that's a little over 6 10,000ths. We have an actual error, because we can calculate the natural log of 1.5, of 0.00443 for a P4. Now what we want is an error of less than 0.000001. So that is far less than the actual and far less than the maximum. And so what we want to do is we obviously have to go out to something that is a higher degree. We need a higher degree than a 4. So that's where we have to take into consideration this definition of how to find the error and say, well, we want to find this, we want to maximize this, but we don't want this maximum to exceed 1.0001 or 1/10,000ths. So we want to be sure that whatever this maximum is, it's less than 1/10,000th. And so in maximizing this, this expression really, it comes into maximizing this expression for the derivative. This is always, the x is going to be 1.5 and c is going to be 1. So those two numbers are going to be fixed. This number is going to depend upon what it's going to take to get this to this below 0.0001. So we have to really look at the expression for the derivative, and we have to find the nth derivative. Okay, we have to find an expression for the nth derivative, and then we have to rewrite that for the next derivative, because that's what this is saying. It's saying the remainder for a nth degree polynomial is the next derivative over the next factorial times x minus c to the next power. So, so we really have to find this pattern here. So if we take a look at the fourth derivative, and I'm going to write this in terms of z. If we take a look at the fourth derivative, that is our minus 6 over x to the fourth power. If we take a look at the fifth derivative, that's our 24. That is our 24 over z to the fifth power. Let me correct the one above it, because this should be a z. Z to the fourth power. And let's take a look at our sixth derivative. So our sixth derivative is going to be negative 120 over z to the sixth power. So taking a look at that, just looking for the patterns, we can see that the power matches the derivative. Okay, so if I'm coming up with an f for the nth derivative of z, then I know that my power is going to have to match the derivative. It's going to have to be an x to the n for the nth derivative. Okay, and then my numerator here, this is a 3 factorial. Let me make that a different color. This is a 3 factorial. This is a 4 factorial. This is a 5 factorial. So the factorials are always one smaller than the derivative. So 1 smaller than n is n minus 1 factorial. And so we have an expression then that for the nth derivative, I'll reduce the n by 1, put the factorial in front of it, and then over x to the n. And then we have an alternating plus minus sort of thing going on here. And the alternator is not really that important. We can put it in, let's see, I have to have a negative sign when I have a positive derivative. Excuse me, a negative sign when I have an even derivative. So that's going to be a negative 1 to the n plus 1. That way I have a 1 to the 5th on a fourth derivative, that'll give me a negative, a 1 to the 6th on this one, that'll give me a positive. And the reason why the derivative isn't important is because of these absolute value signs here. So we're just going to, the reason why the alternator, excuse me, is not important is because of these absolute value signs here. So here is our nth derivative, the absolute value of our nth derivative. the absolute value of our nth derivative would be then n minus 1 factorial over x to the n. And so the absolute value of our n plus 1 derivative then would be just making these all 1 bigger. So n minus 1 plus 1 is just n, and x to the n power becomes x to the n plus 1 power. And so that becomes this portion of the numerator here. Let me go back and just make a slight correction here, because these should be z's. So these should be z's. Okay, now we have to take a look at what maximizes this. Should our z equal c, which is 1, or should our z equal x, which is 1.5? So that's the next question. Okay, and so which one creates a maximum? So which maximizes? Okay, and so z being in the denominator here, this is in the denominator, this one is going to maximize it then, because you want to divide by a bigger number. And so our fn plus 1 to the of z is going to be n factorial over 1 to the n plus 1, which is just going to be 1. So our maximum value for the derivative is just going to be n factorial. And so now we can plug that into our expression for the derivative. So that's going to be n factorial over n plus 1 factorial times x minus c to the n plus 1. So that's what we have to keep less than 0.0001. And so if we simplify this, we'll come back to this question in a bit. If we simplify this, that is x minus c to the n plus 1 over n plus 1. That's how that cancels out, because this is n plus 1. If you remember about factorials, this is n plus 1 times n factorial, and so the n factorials cancel. And so we have to keep that less than 0.0001. So I'm just going to put this in y1 and grab a table here. So coming over here, opening up a new calculator, going to y1, and so just a reminder, our x is 1.5, our c is 1, and so we're going to look at graphing that. And so we have, I'll just put that in as 1.5 minus 1, raise that to the quantity x plus 1 power, and divide that by the quantity x plus 1. And when we look at the table here, we can see that fourth degree, here's our fourth degree polynomial, right? We were off by 0.00625, right? That was our maximum error found up in part C. So there's that maximum error. Fifth degree is still too big. Sixth degree is still too big. So 0.0001 is 1 times 10 to the minus fourth. So those are all still too big, and we're finally getting to something that is small enough. So if this is 1 times 10 to the minus 4, then if we go right here, that's where 1 times 10 to the minus 4th falls. 8 is too big. 9 is the point at which it falls underneath that value. So what that means is that we need to have a 9th degree approximation. So we need a 9th degree polynomial to get an error of less than 1/10,000th. So that being the case, then we need to take this polynomial approximation out. Where is that polynomial approximation? I guess I don't have it on this page. But we need to take this polynomial approximation out to a 9th degree polynomial to get a 9th degree polynomial to get an approximation that is less than 1/10,000th. Now, keep in mind that a 9th degree polynomial means that x to the 9th power, okay, has to appear in a polynomial expression. Because we start with a 0th power term, in other words, we start with the value of the function at the center, that actually means we have 10 terms that are listed. So to address this final question, then, functions we commonly deal with in regards to polynomial approximations, natural log is one non-polynomial expression that we approximate a lot. Also, e to the x we saw is something that we'll approximate a lot since taking derivatives is so easy. Same with trig functions like sine x and cosine x. Again, we'll approximate those. Also, 1 over things like 1 over x or 1 over x plus 1 or stuff like that. Those are not polynomial either. So, and those are all easy things to take derivatives of. So we will deal with those approximating these non-polynomial functions with polynomial expressions. When it comes to natural log of x, we have to center this at 1. These we can center at 0 because they're all defined at 0, so we typically center those at 0. This is not defined at 0, so we have to center this at 1 again. And this we can kind of, we really can't center this, or we can center this at 0 or 1, it doesn't matter. And I've seen that done equally both ways. So just to kind of give you an idea of some of the centers as well.